So the last topic I'll mention here is in Ramsey Theory. This was the topic of my thesis, and chapter 20 of our text is devoted to the subject. So you can read about it there to get a handle on starting a problem in this topic. There are lots of unsolved problems in this field, including some from my own research projects. So as a brief introduction to Ramsey numbers, Ramsey's theorem says that given two positive integers s and t, there exists a positive integer n, such that every red-blue coloring, so here we're talking about edge colorings of the complete graph, every red-blue coloring of the edges of kn results in either a red ks or a blue kt. So Ramsey's theorem tells us that there is always some positive integer, some large enough complete graph, such that every red-blue coloring admits either a red ks or a blue kt. The Ramsey number of s and t, denoted r of s and t, is the smallest positive integer n, for which every red-blue coloring of the edges results in either a red ks or a blue kt. So the question here is, Ramsey's theorem tells us one positive integer exists, and then the Ramsey number is what's the smallest. By the way, we looked at this in class during the first week. We found that r of 3, 3 was equal to 6. I believe I also mentioned then that r of 5, 5 is unknown. It's between 43 and 48, our best known bound. So a lot of research is devoted to the subject of just finding better bounds for these Ramsey numbers. There's a lot of great history that goes along with this that you could add as color for your project. And then there's lots of variations of these, because these are, in general, very difficult problems. And it's hard to do a specific case of this. So there are some variations of this, some generalizations. So one way you can generalize this is for two graphs f and h. The Ramsey number of those two graphs is the smallest positive integer n, such that every red-blue coloring of kn results in either a red f or a blue h. So you need not be searching for small complete graphs that are colored either red or blue, but just any two graphs in general, and this number always exists, and the goal is to find the smallest. That's the Ramsey number of f and h. So that's one generalization. There are some infinite classes of graphs that have been solved for this. You can also generalize this problem by considering more than two colors. So look at red, blue, green colorings of Km that admit either a red F, a blue H, or a green, G, something like that. So you can generalize this to more colors. That's an even harder problem. One variation of this problem I studied for my thesis, and these are called proper Ramsey numbers. So take two graphs F and H, where the chromatic index of H is equal to T, so the fewest number of colors required in order to produce a proper edge coloring of H is T. Then the proper Ramsey number of F and H, denoted PR of F and H, is the smallest positive integer n, such that any T coloring, so using the same number of colors required to give a proper coloring, of Kn results in either a monochromatic, so all edges the same color, of F, or a properly colored H. So I looked at this for a few classes of graphs. We got a few, but there's a lot of classes of graphs that we did not look at and that you could. So the last topic I'll mention is the down arrow Ramsey set of a graph. And so this was in a recent project that myself and my colleague, actually Alexis Byers, that I had mentioned before. We invented this topic and then studied it. We kind of turned the definition of Ramsey numbers on their head. And so we defined it as, given a graph G, the down arrow Ramsey set of G, we denoted this down arrow of the graph, is the set of all graphs F for which every red-blue coloring of the edges of G results in either a red F, or a blue F, so a monochromatic F. We don't have two graphs here. So that is, we look at the collection of all graphs such that any red-blue coloring of G results in a monochromatic F. It turns out that this set of graphs has a sort of algebraic structure to it. It's what's called a partially ordered set, and we determined this down arrow Ramsey set for some small complete graphs for cycles and paths. We looked at this for a few different classes of graphs. And really, this is the principal goal right now in the topic, is to just determine this down arrow Ramsey set for complete graphs, bipartite graphs, and some infinite classes of graphs. So if you're really interested in the subject, please let me know, and I'll send you some papers that you can look at. If you do want to do this as your topic, I'll say that this will require quite a bit more work. So only choose this topic if you want to put a lot of work into the project more than other topics, or if, say, you're taking this class for honors credit. This would be a good topic for you. All right, that's it. That's the end of my presentation. Hopefully that inspired you a little bit, gave you some ideas of some topics you can look at. Again, don't feel compelled to have to pick one of those problems. You can do some searching around yourself, but only search around for the next week or so, and then make a decision and start working on this. All right, that's it.